physicists worldwide brimmed with anticipation as they witnessed the long-awaited activation of the most advanced high-energy particle collider. After patiently waiting for decades, they finally beheld this remarkable invention, poised to transform our comprehension of the universe. The Large Hadron Collider, constructed by the European Organization for Nuclear Research, became operational in September 2008 after a painstakingly protracted construction phase. However, it took the machine's inventors several years to perfect it. Since then, the Large Hadron Collider has played a pivotal role in unraveling numerous enigmas of the universe during its various experimental runs. Nevertheless, recent developments have raised concern among scientists at CERN. Upon ramping up the Large Hadron Collider to a new peak energy level, they detected something unexpected and terrifying. Subsequent investigations have led to various theories attempting to explain this phenomenon, but as of now, they remain unverified and speculative. The universe has many unexplained mysteries, and over the years, scientists have devoted their time to research, in an attempt to understand and explain some of them. These mysteries include the massive black hole found in space, which is said to have an intense gravitational pull that even light cannot explain, and also what lies underneath the Bermuda Triangle, called the Devil's Triangle, is popular for the mysterious disappearance of more than 50 ships and 20 aircraft, but they remain unexplained due to the limitations in technology. In the early 20th century, physicists looked for new ways to explore the fundamental building blocks of matter, and in 1932, physicist John Douglas Cockcroft and engineer Ernest Walton constructed the first operational particle accelerator. These particle accelerators are essential tools for exploring the fundamental constituents of matter. By accelerating particles to high energies and colliding them, scientists can study the resulting interactions and probe the fundamental forces and particles that make up the universe. Given how useful particle accelerators can be in explaining the mysteries of the universe, CERN has constructed the world's largest particle accelerator, but scientists have just made the horrible discovery that this particle accelerator would likely cause the Mandela effect because of its ability to alter the fabric of space and time. What is the implication of this discovery? Many people wonder why they remember things differently from how they happened. Well, this is a phenomenon known as the Mandela effect. The term was made up in 2009 by Fiona Broome. She found out that she and many others wrongly thought Nelson Mandela had died in the 1980s, but he died in 2013. Several factors can cause this effect, such as false memories and the strong influence of social media and the internet, but certain scientists have raised concerns that previous power-ups of the LHC have also caused the Mandela effect. Before dismissing this discovery as a conspiracy theory, note that some prominent scientists and other notable figures have raised concerns. Stephen Hawking was one of the first to express his concerns about the effect of the Large Hadron Collider. He warned in an interview that the collider could create black holes, which could threaten the universe. Another scientist, Dr. Carlo Rovelli, shared his concerns about the LHC in a blog post, suggesting that it might create strange particles, hypothetical particles that can change surrounding matter into something new. Concerns even figures outside of science have spoken about the potential dangers related to the Large Hadron Collider. Astrophysicist Carl Sagan and science fiction writer Arthur C. Clarke also voiced worries about the collider, suggesting the creation of strangelets or even a black hole that could swallow the Earth. In a press conference, President Obama also expressed his concerns about the collider causing a catastrophic event that could affect space and time. The fact that several groups of important people, from scientists to writers and public figures, expressed unease about the LHC highlights the seriousness of the concerns. While we can't predict the consequences, it's crucial to carefully consider the potential risks and make informed decisions about operating the collider. So, is CERN's LHC capable of causing the Mandela effect and other changes in our universe? The Large Hadron Collider is currently the biggest and most powerful particle accelerator in the world. It was built between 1998 and 2008 in collaboration with over 10,000 scientists across more than 100 countries. It became operational on September 10, 2008, and is the newest part of CERN's accelerator complex. The goal of this particle accelerator is for physicists to test the predictions of different theories of particles, including measuring the properties of the Higgs boson, searching for the large family of new particles that were predicted by supersymmetric theories, and studying other unresolved questions in particle physics. The collider looks like a 27-kilometer circle that is made of strong magnets and structures that make particles go faster and gain more energy. Inside the accelerator, there are two beams of high-energy particles that move at an incredible speed, almost as fast as light, before they are directed to collide. These beams travel in opposite directions through separate tubes called beam pipes, which are kept at extremely low pressure. The beam pipes then follow a circular path around the accelerator due to a powerful magnetic field that is generated by the superconducting electromagnets. The magnets are made from coils of special electric cables that operate in a superconducting state, allowing electricity to flow without resistance or energy loss. To maintain this superconducting state, the magnets need to be cooled to a temperature of -271.3 degrees Celsius, which is colder than outer space. To achieve this, a system of liquid helium is used to cool the magnets, along with other necessary supply services throughout the accelerator. Running at an energy of 6.5 tera-electron volts per proton, the LHC accelerates protons from 450 giga-electron volts to 6.5 tera-electron volts. During this process, the magnetic field of the collider is about 100,000 times stronger than the Earth's magnetic field, and it requires about 120 megawatts of electricity to operate, which is enough to power a small city. Superconducting dipole magnets in the Large Hadron Collider increase from 0.54 to 7.7 teslas, reaching an impressive collision energy of 13 tera-electron volts. At this energy level, protons attain a Lorentz factor of about 6,930, moving at a velocity of approximately 0.999999990 times the speed of light. The time for a proton to complete a full orbit around the main ring is less than 90 microseconds, resulting in an astonishing 11,245 revolutions per second. The journey of protons in the LHC begins in a linear particle accelerator, LINAC 4, generating negative hydrogen ions at 160 megaelectronvolts. These ions move through the proton synchrotron booster, where electrons are stripped away, leaving only the nucleus with a single proton. Subsequently, the protons are accelerated to 2 gigaelectron volts and enter the proton synchrotron, reaching an energy of 26 gigaelectron volts. Finally, the superproton synchrotron boosts its energy to 450 gigaelectron volts before injection into the main ring. In this ring, protons are accumulated, accelerated to their peak energy over 20 minutes, and circulated for 5 to 24 hours, allowing collisions at the 4 intersection points. While the primary focus of the LHC physics program is proton-proton collisions, it dedicates periods, typically 1 month per year, for heavy ion collisions. Lead ions are the preferred choice, accelerated to an energy of 2.3 tera-electron volts per nucleon or 522 tera-electron volts per ion in the LHC ring. The LHC operates with significant energy consumption, drawing about 200 megawatts from the French grid during operations, roughly 1/3 of the energy consumption of Geneva. The LHC accelerator and detectors contribute around 120 megawatts to this demand. This energy surpasses that achieved by the relativistic heavy ion collider. The heavy ion program aims to explore quark-gluon plasma, providing unique insights into the fundamental nature of matter and the cosmos. One of the major theories in particle physics, concerning the existence of the Higgs boson particle, has been proven with the help of this particle accelerator. The Higgs boson, often referred to as the God particle, made its appearance at CERN in 2012, marking a significant breakthrough in the field of particle physics. Named after Peter Higgs, the Higgs boson is a subatomic particle in the standard model of physics produced by the atomic activation of the Higgs field. The Higgs field, shaped like a Mexican hat, is an invisible force field that affects the way particles interact, giving them mass through something called the Higgs mechanism. The masses of the Higgs boson and top quark are important in determining the stability of the vacuum that houses the universe. According to the standard model, if the universe is in an unstable vacuum, it could lead to significant changes in the distant future, altering everything we believe and understand about the universe. Extensive scientific research has been done to check if there are connections between the Higgs field and the Big Bang, with theories proposing that a fundamental atomic field, such as the Higgs field, could be responsible for the rapid expansion of space during the universe's early moments, known as the inflationary epoch. Scientists use a special kind of collider, the electron-positron collider, to accurately measure the mass of the top quark and predict the future of the universe in case the vacuum's stability changes. The Higgs field, believed to fill up the vacuum, influences the extreme energies of the universe's early moments and creates the forces seen in the universe through changes in its structure over time. However, there is a discrepancy between the energy found in space, which is very close to zero, and the energy predicted by theories involving the Higgs field, leading to the cosmological constant problem. In the 1960s, scientists faced challenges in unifying the electromagnetic and weak nuclear forces using quantum field models. Theories predicted particles known to have mass should actually be massless, causing a theoretical problem. Martinus Veltman and Gerard T. Hooft made significant progress in fixing these issues, leading to a widely accepted theory and changing the way particle physics is viewed. Studying the Higgs field involves its potential involvement in the Big Bang, its effect on the universe's stability, and its connection to vacuum energy. The efforts of scientists throughout history have resulted in theories and models that enhance our understanding of the cosmos. Understanding the strong force and the interactions between quarks and gluons through the study of hadrons is crucial for explaining mysteries like dark matter and the matter-antimatter imbalance in the universe. While the Large Hadron Collider, LHC, has not been scientifically proven to cause the Mandela effect or create cosmic black holes, it is essential to recognize its power in solving cosmic mysteries and understanding our planet better. Unwarranted claims about the LHC's effects on the cosmos can have negative consequences.